Hooke's law. In physics, Hooke's law is an empirical law which states that the force, F, needed to extend or compress a spring by some distance, x, scales linearly with respect to that distance. That is, F sub s equal to kx, where k is a constant factor characteristic of the spring, that is, its stiffness, and x is small compared to the total possible deformation of the spring. The law is named after 17th century British physicist Robert Hooke. He first stated the law in 1676 as a Latin anagram. He published the solution of his anagram in 1678 as ut tensio sic vis, as the extension so the force, or the extension is proportional to the force. Hooke states in the 1678 work that he was aware of the law since 1660. It is the fundamental principle behind the spring scale, the manometer, the galvanometer, and the balance wheel of the mechanical clock. The equation holds in many situations where an elastic body is deformed. An elastic body or material for which this equation can be assumed is said to be linear elastic or Hookean. Hooke's law is a first-order linear approximation to the real response of springs and other elastic bodies to applied forces. It fails once the forces exceed some limit, since no material can be compressed beyond a certain minimum size or stretched beyond a maximum size without some permanent deformation or change of state. Many materials will noticeably deviate from Hooke's law well before those elastic limits are reached. The modern theory of elasticity generalizes Hooke's law to say that the strain, deformation of an elastic object or material is proportional to the stress applied to it. However, since general stresses and strains may have multiple independent components, the proportionality factor may no longer be just a single real number, but rather a linear map, a tensor, that can be represented by a matrix of real numbers. In this general form, Hooke's law makes it possible to deduce the relation between strain and stress for complex objects in terms of intrinsic properties of the materials they are made of. For example, one can deduce that a homogeneous rod with uniform cross-section will behave like a simple spring when stretched, with the stiffness, K, directly proportional to its cross-section area and inversely proportional to its length.